Okay, so we've laid the groundwork in terms of energy and in terms of enthalpy, and we should be able to use a balanced chemical equation where the enthalpy for that reaction is given to us to figure out the amount of heat given off or consumed given a certain mass of starting material. However, what if we're not given the enthalpy for the reaction? How do we actually measure the change in enthalpy for a reaction? Well, it helps to remember that enthalpy, H, is really just the heat at constant pressure. And change in enthalpy is simply the change in heat at constant pressure. So we have some tools for measuring change in heat. And we'll go through some of those here in kind of a stepwise process. We need to add a couple more definitions and terms to our toolbox and one or two equations, but I think that it will make a lot of sense. The way that we actually measure enthalpy change for a reaction is a process known as calorimetry, and I'll go through what that means. So within this process of calorimetry, measuring enthalpy change for a reaction, there are some definitions. There's heat capacity, which is given the symbol capital C, and then there's specific heat, which is the heat capacity with a subscript S. What are those definitions? Well, the heat capacity is the amount of heat required to raise an object's temperature by 1 degree Celsius. However, it's sometimes more convenient to have a specific heat, and that's simply the heat capacity of specifically 1 gram of material. So this now incorporates mass into the equation. And we can write an equation for the specific heat as being Q, the heat, divided by the mass of the object times the change in temperature. Change in temperature is always final minus initial here. And this gives me an equation where I could actually measure the specific heat for an object or for a metal, providing that I was able to measure the amount of heat or knew how much heat I was giving into an object. However, since in many cases, what we're talking about here is that we don't know the amount of heat, what would be more useful from this equation is that we could use this equation if we knew the specific heat and the mass and the change in temperature, we would be able to then measure the amount of heat put into the reaction or given off. Now, many of these specific heat values have been measured in various ways and reported in tables. So here's just an example of the specific heats for a whole number of compounds and molecules. So water has a specific heat of 4.18 joules per gram degree Kelvin, where 1 Kelvin is also just change in 1 Kelvin is also equal to a change of 1 degree in Celsius. So as mentioned, if we rearrange this equation, we now have a useful equation for determining the amount of heat that flows in a reaction. So Q is equal to the specific heat times the mass times the change in temperature. So, okay, we have that equation, but how do we actually do this in practice? Well, we can do it in practice using an actually fairly simple apparatus known as a constant pressure calorimeter, or even just a coffee cup calorimeter. And in this case, you can see if we simply take 2 styrofoam cups and nest them together, then we can have a solution in there and add a cap with the thermometer. The thermometer will directly allow us to measure the temperature of the solution. And so we can just write this equation a little bit more specifically and say that the change of heat, the heat gained or lost by the solution is equal to the specific heat of the solution times the mass of the solution times the change in temperature for the solution. Now, it's important to make one distinction here, that the change in the heat flow for the solution is equal in magnitude but opposite in sign for the reaction. So what we measure, remember, the solution is the surroundings. The system is the chemical reaction itself. We never measure the temperature of the actual chemical reaction. What we're measuring the temperature of is the surroundings, in this case, the solution. So if we do a reaction in water, the actual reaction, right, if we wrote the net ionic equation, if we were doing an ionic reaction or something of that nature, the actual reaction is between molecules, but then that heat is absorbed by the surroundings. If it's given off by the reaction, then it's absorbed by the surroundings. And so the magnitude is equal, but the sign is opposite. So just keep that in mind as we go forward. All right, and just remember that the Q of reaction, that is the actual enthalpy. That's what we're looking for. So let's do an example. What does this look like? We can also rearrange, we can kind of rearrange our previous equation. So if I go back one slide, right, we have Q is equal to specific heat times mass times delta T. But if we're trying to find delta H, and that's equal to Q of reaction, and Q of reaction has the opposite sign of Q of solution, then I can rewrite my equation here as simply delta H is equal to minus the Q of solution, which is equal to just minus the, or negative of the specific heat times the mass, the specific heat of solution times the mass of solution times the change in temperature. All right, so we have this example here where we've got 6.5 grams of solid sodium hydroxide is dissolved in 100.0 grams of water in a coffee cup calorimeter. The temperature increases from 21.6 degrees Celsius to 37.8 degrees Celsius. Calculate the change in enthalpy for dissolving sodium hydroxide. Well, the change in temperature is just going to be the final temperature minus my initial temperature. And so that gets me one variable. The mass becomes the overall mass of solution. So it becomes the mass of water and the mass of the sodium hydroxide. And then the specific heat here, well, it's the specific heat of the solution. In this case, we can take that to be simply the specific heat of water. So let's go through this here. We've got our equation. The specific heat is the specific heat of water here. That's the majority component of our solution, so we'll take that to be just the specific heat of the solution. The mass is the sum of the two masses because that's the total amount that's undergoing the change. And then the temperature is simply final temperature minus initial temperature, and so we have now a change in temperature of 16.2 degrees Celsius. It's important here to note that changes in degrees Celsius are equal to changes in Kelvin. Not absolute. An absolute value of 16.2 degrees Celsius is not equal to 16.2 Kelvin, but a change of 16.2 degrees Celsius is equal to a change of 16.2 Kelvin. It's just very important to keep that in mind. If you took 16.2 as an absolute value and then tried to convert that to Kelvin, you would come out with a large number for Kelvin because you would add 273.15 degrees, but it would throw the equation completely off. We're talking about a change in temperature, not absolute temperature. All right, we have those three values. We can simply plug them into our equation, and we come out with now a final value of negative 7.21 times 10 to the third joules for our change in enthalpy for this reaction. Now, one other thing to note is that although we just expressed that in terms of joules, enthalpy is most frequently expressed in terms of kilojoules per mole. So how do we do an example of that? Well, let's take this same example we just did, but let's express it now in terms of kilojoules per mole. So we had it in joules. We will express that in terms of kilojoules. Our delta H was negative 7.21 times 10 to the third joules. we can convert that to kilojoules fairly easily. 1,000 joules in a kilojoule, you do the conversion, and it's just negative 7.21 kilojoules. Now, the per mole, well, what is it per mole of? It's per mole of sodium hydroxide. It's not per mole of water, it's per mole of sodium hydroxide. So I have a mass of sodium hydroxide. I can calculate the molar mass simply by adding up the atomic weights, and I can convert and find the number of moles of sodium hydroxide that I have present. So that's fairly simple. 6.50 grams of sodium hydroxide divided by 40.00 grams of sodium hydroxide per 1 mole. And I'll come out with 0.1625 moles of sodium hydroxide. I can carry the extra decimal place until I get to the very end of my calculation. And now I have an amount in kilojoules and I have a number of moles. So I simply take the kilojoules and divide it by the number of moles, and I will come out with a change in enthalpy of negative 44.4 kilojoules per mole. This is very useful now because it allows me to, if I know the enthalpy of reaction in terms of moles, in terms of kilojoules per mole, then I can easily calculate how many kilojoules I would generate based off of, or how much heat I would generate based off of any given mass of sodium hydroxide, which I could then convert to moles and multiply by this value.